بسم الله الرحمن الرحيم. طيب, we will go back to cover the counter that we skipped. طبعا before that, when we talked about counter, we took a look at all kinds of counter that we can implement, or those that we implemented already in Unit 2. We saw how to implement them يعني using logic, and now we'll see how can we model them in Verilog. تمام. ف we looked at many counters اللي هو normal counter. طبعا هذه كلها this was a synchronous counter. We had ripple counter and synchronous counters. بالنسبة للsynchronous counter, we have an adder that will feed into our flip-flop, and the result will be fed back to the adder, and this adder will just add 1. فبالتالي we call this circuit an incrementer. تمام. And we saw in Verilog all we need to do is that we assign Q plus 1 to Q in the next clock cycle. One very important thing to note is the reset signal. When we check on it, if it's a normal counter, we'll just reset it to 0. طبعا a reset signal depends if it's an asynchronous or a synchronous signal. In this code, this is an asynchronous reset with an active high reset. To differentiate between, if the question did not determine or did not specify by writing active high or active low, we should know that from the name of the signal. إذا كتبنا reset, meaning we want an active high reset. معناته if it's 1, reset. If it's 0, do not reset. Or we can write reset n. Reset n, meaning this is an active low reset signal. So if it's 0, reset, and if it's 1, continue normal operation. تمام. So we don't need to specify in the question active high or active low. By reading the name of the signal, you should know if I want an active high or an active low. And question 2 in the homework يعني will give you some practice on that. So make sure you read the name of the reset signal, because we're going to use this as a standard. طيب, we saw also this is a counter with an enable signal. So first we're going to check on the reset, and then we're going to check on the enable signal. If the enable is 1, we're going to count. If the enable is 0, we will not count. Q will just hold its old value. We added also a parallel capability of parallel load to the counter. So if you don't want to start from 0, let's say you reset, and then you want to start, this is a 4-bit counter, and you want to start the count from 4, for example. So at your input R, which is the parallel load input, we're going to have the value 0, 1, 0, 0. And then we're going to raise the signal L, which is load. So it will come here and check for L. If we are loading, we're going to just load the value of R into Q. If we're not resetting and we don't need to load, we can enable the counter and count. Okay. You can also implement a down counter by changing the assignment from Q plus 1 to Q minus 1. And I think we also looked at an up-down counter where the count can be either a +1 or a +0. This is one implementation of it. You can also have it as inside your count condition. So you're going to say else if E, which is count. You can say if up down, which is the signal that will determine if you're counting up or counting down. So if up down, I think here if up down is equal to 1, that means count up. So if up down equal 1, count up. If up down equals 0, this is count down, and this is count up. So you can either implement it like the way it's implemented in the slides using conditional statement, or and if this is more clear to you, inside your else if you can have another if statement which will say if up down, make it Q takes on the value of Q plus 1, else Q will takes on the value of Q minus 1. In terms of synthesis, this code and this code will synthesize the same. It will all create a 2 to 1 multiplexer for that. Okay, طيب. We have three counters, that special counter that we talked about in Unit 2. As a reminder, we have the ring counter, we have something called the Johnson counter, and we have the linear feedback shift register, which is used for random number generation. We will start with the ring counter. So the ring counter will start at a state, like in a 4-bit ring counter, you start at this state, either 1000 أو 0001. يعني يعتمد are you shifting right or left. Next clock cycle, this one will go into 0100. So what you're doing is you're basically shifting the 1 up to the last bit. الفرق بين الشيفت register and this counter is that in a shift register, after this state you should get all zeros. تمام. لكن هنا لا, from this state you're gonna move back to the first state. So this one will be rotated to the first or the most significant bit. تمام. One small remark about this implementation and these states, these are not, I mean, this state progression is not meant for this circuit. Check now. Here I have Q0. Let me let's take it one by one. So the start signal will set this value A. فبالتالي this counter will start at 1 0 and then up to 0 depending on how many bits you have. تمام. ولكن لاحظ انه هذه Q0. تمام. This is not the MSB. هنا we started by setting the MSB to 1. تمام. if you want the same progression, you need to change that to make the reset signal go into setting the most significant bit. تمام. what I'm saying انه هذا a design will not give you this progression. This design will give you the following progression. It will start from 0001 because this is Q0 and this is Q to n minus 1. تمام. But it will work the same way. However, it's going to be shifting left instead of shifting right. So it will start from 001, goes to 0010, then 0100, and then 1000, and then back to 0001. Okay. So please note that this progression is not going to be implemented using this implementation. Okay. طيب. فبالنسبة للكود, let's check the circuit and see what needs to be done. There are two things that you need to do. First, the reset signal. الريست signal هنا it will not reset to zeros. لاحظ أي progression of any ring counter will not have all zero state. So that's the first thing to do. When you reset, you need to make sure that you are either resetting to 100 أو 0001 depending on the direction of the ring counter. تمام. if you reset at 0001, oh sorry, here it's resetting to 1000, that's one thing you need to take care of. And reset is not resetting to 0. Now, if you're not resetting, you can do this two ways. Either by, if you come here, you can check now if this is Q0. Q0 is reading Q of n minus 1. فبالتالي you can write Q0 takes on the value of, اعتبر انه عندنا 4-bit counter, it's reading Q3. And then Q1, this is Q1 is reading from Q0. Q2 gonna read from Q1. And then Q3 will read from Q2. Okay, so you can do that. أو إنك تستخدمها in concatenation form. You say Q will take on the value of the most significant bit, which is Q3, is reading Q2. Q2 is reading Q1. Q1 is reading Q3. فبالتالي for the three most significant bit you can write this is gonna read Q from 2 to 0. تمام. It's gonna read from Q2 to 0, and then the least significant bit, which is Q0, is reading Q3. So you plug in Q of 3 here. Okay. طبعا هذا for this example. This code is doing it the other way around. لأنه هذا الكود قلنا أو هذا الimplementation is doing 001 0010 0100 and so on. تمام. ولكن this code is starting from 100, so we need to shift right. بالتالي you are resetting Q3. This is Q2, Q1, Q0, and then Q0 will be connected to Q3, and we are resetting Q3. This is the reset. تمام. if you write the code, you'll say Q3 will take the value of Q0, Q2 is taking Q3, Q1 is taking Q2, and Q0 is taking Q1. You can write this, or if you want to do it in concatenation form, it's going to be as follows. Q3 is reading Q0, so I'll post Q0 for the MSB. And then from 2 to 0, we're going to read 3 to 1. So we'll just post Q3 to 1 right here. So these two codes are equal. Okay, so make sure that when you solve any ring counter problem, to read the specification. If I give you, I want this progression, تمام, you're going to use this code. ولكن if you are going with this progression, which is shifting to the left, that's going to be a different code. So the easiest way to do it is draw the circuit and then read your assignment from that circuit. Second important thing about ring counter is to know what are you resetting to, because if you reset to all zeros, it will not work. Okay, هذا بالنسبة لي الring counter. This is a test bench for the ring counter, so we can go through it very quickly. We're going to define rigs for the clock and reset, and we need a wire for the output, 4-bit output Q. We're going to make an instance of the counter. We're going to connect clock, reset, and Q to our module. And then we need to create a loop for the clock. So we'll start with clock equals 0, and then use a forever loop. We're going to take 10, so it will stay 10 time units at low and then 10 time units at high. So the whole period is going to be 20 time units. This is very important to understand when I ask you to generate a clock with a certain frequency. تمام. إذا أبغى 20 nanosecond, if I need 20 nanosecond clock, 20 nanosecond clock cycle, you need to define the time scale as 1 nanosecond and use a delay of 10 time units when you create the clock. If you write 20 here, this is going to generate a 40 nanosecond clock cycle. Okay, so that's very important to note. After you generate a clock, you will make another initial block to enter the values. So we only have reset in a ring counter. فبالتالي we're going to put reset equal to 1 because this is an active high reset. And then after 50 time units, which is equal to 50 nanoseconds, we're going to put reset equal to 0 and then watch the value of Q and see how it progresses. Okay, and from this result, it seems that the counter is implementing a shift left operation. You start at 0001. Where is our reset? That's our reset signal. So our reset signal will stay high here. Since the reset signal is high, the value of the counter is going to be 0001. So what they did here is that they said if reset, again, this code, I mean, this simulation is not for this code. تمام? It's the other way around. So what they did here, that if reset, Q will take the value of 0001. That's what's happening here. And then when reset goes down, the counter will start working, changing the value each cycle. And notice that it's shifting the 1 to the left until you reach 1000, which is the final state, and then back to the same state, which is 0001. As long as reset is 0, this counter is gonna keep progressing the same way. Okay, so this is the test result for uh, for a ring counter that is shifting to the left. طيب هذا بالنسبة لي الرينج counter. For the Johnson counter, let's take a look at the sequence before we look at the circuit. So a Johnson counter will start at zeros, and then we'll start injecting ones either from the right or from the left. In this example, it's injecting from the left. So it goes to 1000, and then 1100, and then 1110, all ones. After that, it's going to inject 0 from the left. So 0111, 0011, 0001, and then back to our first state, which is all zeros. For implementation, we're going to reset to all zeros, and then you will put Q bar. I'm not sure why all these implementation are opposite to the progression. This is the same issue. هنا عندنا هذا الكاونتر will start. This counter will reset at zeros. Okay, that's the first state. And then watch what happens in the next state. عندي the MSB. تمام. We are taking Q bar of MSB and putting it into Q0. بالتالي Q0 will read 1. طبعا انا I reset at all 0. this is 0 0 all zeros, and then this is 0. بالتالي Q bar is 1. So you are putting Q bar into Q0. For this implementation will start at all zeros. Next state is going to be 0001. Okay, so this will stay at 1. This will change to 1. Next cycle, that's going to be 0011. After that, it's going to keep progressing up until it reach all ones. When it reach all ones, see what happens. When it's all 1, now MSB is equal to 1. بالتالي Q bar is equal to 0. So now you are injecting zeros to the LSB. بالتالي it will be 1110, 1100, 1000, and then back to all zeros. And then Q bar of MSB will be 1, and you're back to the state. Okay, so for these slides, this slide and this slide, the progression of states is not equal to the circuit implemented here. Okay, they are opposite. Now for the Verilog code. For this case, we're going to use an asynchronous active low reset. So we're going to add negative edge of reset n. And then if you want to reset, if reset n equal to 0, Q here will equal to zeros for a Johnson counter. Okay, you need to know the names. لما اسالك عن ring counter اسالك عن Johnson counter ما حيعطيك الستيتس. You should know how the ring counter works and how the Johnson counter work. Okay. طيب, and then you can do, this is the concatenation form. You can also do it without concatenation form. So This counter wants to go, I think, so this counter will implement the sequence in this way, okay, and so on. So what you do is that we will take Q bar of Q0 and put it into Q3. So Q will read the value of the most significant bit is going to take Q0 bar. So not Q0. And then each bit will read from the one before. فبالتالي from Q2 to Q0 we will read from Q3 to Q1. Okay, so we can just write Q3 to 1 here. If you don't like that, just write it one by one. So Q0 will read Q1, Q1 will read Q2, Q2 will read Q3, and then Q3 will be reading Q0 bar. So not Q0. Okay. These two are the same. So that's for the Johnson counter. Last special counter we have is the linear feedback shift registers. And the LFSR circuit, depending on the number of flip-flops, it will have some XOR implemented in between. So we need to check for the equations. This equation, you'll either be getting the equations or you will be seeing it in the circuit. Like the question in the homework, I gave you the circuit and I'm asking for the code. تمام. For this code, for example, check your assignment to the value of Q. تمام. So here we have 3-bit counter 0 to 2. فعندي, if I want to draw the circuit, I have Q2, Q1, and Q0. Okay, Q2, Q1, and Q0. Now Q2 is reading Q2 this way. Q1 is reading the XOR between Q2 and Q0. I'll take Q0, I'll take Q2, put it in an XOR gate, and then putting the result to Q1. Q0 is reading from Q1. So this is just a connection between these two. Now that's one part of the question that you can get for LFSR. Second question that you can get is the one that we solved in the tutorial. I can ask you about the sequence that this code will generate. So I'll tell you I will reset at 001, for example. And then I'm asking you to give me the sequence of states. طبعا sequence of states يعتمد على ال XORs that you have in your circuit. تمام. But since we have the equations, we can read it from here. We start from 001. This is Q2. So Q2, Q1, Q0. I start from 001. Now the next cycle, Q2 is reading Q2. So that's going to be 0. Okay. Q2 is reading Q2. So that's going to be 0. Wait. I see what's happening here. Yeah, I'm not sure why the code is implemented this way. ولكن I just noticed here that output rig is from 0 to 2. For Q0 is the most significant, and then Q1, and then Q2. Okay. Now the circuit is going to be different. That's some trick that you need to note. Okay. I have Q0, Q1, Q2. Oh, okay, that's going to be different. So Q0, this is Q0 now, and this is Q1, and this is Q2. ليش؟ لأنه الامبلمنتيشن أو التعريف الريك كان from 0 to 2, meaning it's Q0, Q1, Q2. Alright? So the first value here is going to be Q0. ليكون سؤال التوتوريال نفس ال okay, I need to check. Tutorial unit 6. اوكي يا في التوتوريال عرفوا من 0 الى 3. فالسولوشن اللي حليناه المره الماضيه كان خاطئ. تمام. Please resolve the problem using the way that we're gonna solve it now. اوكي. That's يعني ترك عظيم. اوكي. Focus. الآن عرفت Q from 0 to 2. بالتالي الترتيب حيكون Q0 Q1 Q2. اوكي اللي هو عكس المتعارف عليه. بالتالي when I make assignments here, this value will go to Q0, this value will go to Q1, and this value will go to Q2. اوكي فإذا رسمت السيركت, if I have Q2 Q1 Q0, okay, Q0 is reading Q2, Q0 is going to be reading from Q2, so this is going here. Q1 is reading the XOR of Q0 and Q2, so we will have an XOR going into Q1, and then Q2 will read from Q1 this way. Okay, so if I reset to I want to make sure that this sequence is correct. If I reset to all zeros, oh sorry 001, فعندي هنا Q0 Q1 Q2. I'm setting 001. Now let's check the next cycle. Q0 will read Q2. So Q2 here is 1. بالتالي the next cycle Q0 will be 1. Q1 is reading XOR between these two values, so 1 XOR 0 is 1. بالتالي Q1 is equal to 1. And then Q2 is reading from Q1. بالتالي that's going to be 0. Okay, that's cycle 1. Cycle 2. And now for cycle 3, oh, this should be cycle 0 because it's the reset. So this is cycle 1 and this is cycle 2. Now Q0 is reading Q2. بالتالي that's going to be 0. Q2 is reading Q2 is reading Q1, so this is going to be 1. And then Q1 is the XOR between these two values, so that's 1 XOR 0, which is equal to 1. Next cycle, Q2 reads Q0 reads Q2, so that's 1. Q2 reads Q1, so that's 1. And the XOR between Q0 and Q2 is equal to 1, so that's all ones. Next cycle, Q0 reading 1, Q2 reading this one, and then the XOR between these two is going to be 0. Okay, so if you keep on going, you're going to find that you're matching this sequence. Now this sequence should go into a random fashion until it reaches the value that you started with. فبالتالي we started with 1 and then 6, 3, 7, 5, 4, 2, and then 1 again. Okay, so you cycle between 1 to 7 without passing by zeros. Okay, in a random in a random fashion. تمام. So according to this definition, please go back and solve I think is it question 2 or 3 in the tutorial, I don't remember. ولكن في التوتوريال انا حليتها على اساس انها Q 3 to 0. I didn't notice the shift or the switch between these two values because as you saw it's going to make a huge difference in solving the problem. Okay, actually I think in the tutorial we came up with only two states, which is يعني it was weird a little bit. لأنه المفترض any pseudo random number generator it should cycle through all the values ولكن randomly. تمام. If you have 4 bit you should be able to cycle from 1 to 15 randomly, and you can go 1 5 6 11 13 back to 5 يعني إلى أن تصل إلى الفيرست ستيت. Okay. This is for the counters or special counters, the slides that we missed while talking about counters last time. Um, yeah, and hopefully on Thursday we'll solve homework 5 بإذن الله, and we'll finish our يعني we conclude our course. طيب, في أي سؤال؟